Welcome back. Our next speaker claims to be one of just 3 macro-programming neckbeards in existence. Please welcome Alexander Ioffe with his talk about language integrated query for Kotlin.
Thanks, guys, for coming to my talk, which is probably the most mundane and boring talk in this entire LambdaConf. So thank you for being here. And also also you for bearing with me. I've been a far from perfect maintainer of all of the libraries that I've worked on. And so thank you all for bearing with me over the years. I said this before to folks in the lunchroom, but I'll say it again. Today is actually a Jewish holiday. It's second Passover. Now, according to Hasidic thought, Passover is a chance for us to have an exodus from our own personal Egypt, to have an exodus from our own personal constraints, our own personal limitations, and the second Passover is a second chance at doing that. So whenever someone asks me what I see in Kotlin, I say I see a second chance. I see a second chance to build the kind of library, or the kind of libraries that I've always wanted to build in Scala, that I've always wanted to create, but for multiple reasons couldn't. So thank you everyone for coming here. Here's what you can expect. Again, this is the most mundane talk of the entire LambdaConf. There will be SQL. There will be lots of SQL in this talk because, as John likes to say, in order to be able to present a solution to a problem, you have to feel the pain of the problem. So we're going to be feeling the pain just a little bit here. And so I'll talk about why language integrated query is needed. I'll talk about why Kotlin doesn't really have anything right now that solves this problem. And then I'm going to talk about ExoQuery, what ExoQuery is, and the problems that it solves, and talk about what I plan to do with it in the future. So I'll start with my own personal story. My life changed the second that I came, basically my first day on the job in the finance industry. I come to the office, and my manager comes to me and he says, yeah, we've got this EJB J2EE stateless middle tier. It's got some CRUD UIs, but really it's a bunch of nonsense. All the information, all the real logic is in the back end, and it's these 300 SQL queries that are half a page to a page and a half long. And these things are responsible for feeding all of the information from half a dozen different CRUD backends into a stock exchange. And if any of these 300 queries are wrong, the stock exchange crashes or it fails to start up and millions of dollars are lost. And of course, because we're structured as an organization the way we are, you are the only person that is ever going to know about these 300 queries. You are the only person who is going to care. And yeah, don't screw this up. Goodbye. And that was basically my very blunt introduction to this field. So I started looking at these 300 queries and pondering my various life choices over the years. And I realized that this is not 300 queries. This is like 30, but there are 10 variations of each, and the variations are there because it's impossible to abstract the SQL. And that set me on the path of Slick and eventually Quill and this entire thing that I've been banging my head on for the past, better part of a decade. So I'm going to actually make you feel the pain of this a little bit. So everybody, look to the neighbor to your right, look to the neighbor to your left. If it is within the bounds of propriety, take their hand, grip it tightly, and here we go. All right, so I saw something like this, and I'm like, okay, these are the common parts in magenta. The ones that aren't common are in yellow, so we're pretty darn sure this is the same freaking query. Okay. And not only that, but it actually does have some independent parts, merchant clients and service clients. Again, I have modified this data from its original form because of, NDAs, but you can extrapolate what this might have been. But anyway, so, all right, merchant clients and service clients, we have some inner projections, and we have a union of inner projections, and we have an outer projection, and those outer projections have a bunch of other things on the bottom. And those things ultimately join onto some other things with some incredibly complex conditions that I really don't want to go into because nobody cares. Okay, now the first thing that anyone in the field tells me is, oh, use CTEs, right? Okay, move all the garbage from the query from the bottom of the query to the top of the query. Okay, right, like this is a solution. Okay, we need views, and this is where everyone tells you to go eventually. All right, so here's one view, here's another view. We take that view, we have an abstracted view of the joined view. We take that view, plug it into the primary view, and voila. Right, there's our abstraction. We have solved the problem. Actually, we haven't. The second that we have a new variation of any of the input data to any of these flows and any of these subflows, immediately you need to replicate every single downstream dependency, which means that your code effectively doubles size of every single variation that you need to have. Great. Okay? So then you start dealing with really sophisticated solutions like, oh, we need table returning UDFs, we need to have all the components that we're using in all of our possible data flows, and we need to union them and normalize them into all these UDFs, and we'll use a bunch of complex switches to control them, and then we'll propagate these switches from table returning UDFs into other returning table UDFs, and yay, we'll have abstraction. Yeah, this doesn't work. This doesn't work because you have to propagate every single parameter across all of these UDFs, so you have an unsustainable amount of propagation of parameters. And effectively, when you have other kinds of business units that need other parameters that get repropagated, the amount of parameter repropagation effectively kills you. But even before that kills you, the fact that you need to be able to take unions, and the fact that you need to be able to extract data from all these unions of subunions will kill you first. Because guess what? Deeply nested queries really suck in terms of performance. So this is completely untractable. Okay? Now, what do we actually want? What do we actually need? Well, we need frickin' composability. We need the ability to be able to say, this query is composed of other queries, right? And in collections, this is our expectation, something like this, right? We have some kind of computational unit that produces a collection of things, and that thing goes into something, and that something potentially joins a bunch of data or does some other stuff with it and returns some other thing, right? Because then what we could do is we could just take our inner pieces and compose it with our outer piece. Except for one problem. Polymorphism, right? There's no such thing as polymorphism in databases. Okay? So this is a Sisyphean task. It is a Sisyphean task to do this in views. And by the way, this is like, you know, in the past you had these RDBMSs, right? Like now we have data warehouses, we have Amazon Redshift and Spectrum and Snowflake, right? We have Snowflake, the future of all analytics, Snowflake, that takes this freaking problem and like amplifies it by 10 times, right? In RDBMSs, at least some of these performance limitations we could live with. Sorry, with 100 billion rows in Snowflake, not a chance. Okay, no database can do this, and no distributed database can do this. None of the current offerings from any of the data warehousing solutions can do this. Nobody can do this on the level of SQL. So of course, we try and look to higher level languages to solve this problem, and yay, Kotlin, do we have a solution for this in Kotlin? And we don't. We actually don't. I looked at Kotlin libraries, I looked at KTorm. KTorm doesn't support inner tables with nested aliases. Exposed can sort of do it, but you have to drag it over the finish line. So again, let's feel the pain, and let us drag it over the finish line. Okay. All right, so we have these table values, right? We can't use normal columns, so we have to use these things. All right, let's create these two. Let's create these two. Let's create the union, alias the union, take this, pass it into the outer query, right? We solved the problem? No, actually, I haven't shown you the types. This is a completely untyped thing. You have no clue what frickin' columns are inside. Okay, so what is the dot? What comes after the dot? Oh, we need to create a fake table. We need to create a fake table whose name happens to be the same as our alias. We take that fake table, we name it the same as our alias, we take that table, we plug it into the main part of the query, we take that, okay, it repropagates. Ooh, but wait. We hard-coded the name of the inner alias of the query. Whoops! Oh, I have an idea. We'll pass it through the constructor. We'll pass it through the constructor. We'll put it in there. We'll name it to the same thing as the alias, and voila. This whole thing will work. Okay? Yeah, sorry. At this point, we're just dragging this over the finish line. This is not what the system was designed to do. The system was not designed to do deeply nested query composition. There are things that Expose does well, but deeply nested query composition is not it. This is like the thing that we're selecting columns from is just not the same thing. Like this thing that we're selecting columns from, this thing that we're selecting columns from is not the thing that is actually being used here. Sorry, we're dragging this over the finish line. This is not the function that we're looking for. What goes into this thing? What comes out of this thing? Remember, this is the expectation. Sorry, this is not it. This is not the composition function we're looking for. Okay? Now, before we go further, right, let's look at DSL land, right? This is DSL land. We've got all these interesting things that have all of these interesting column types, right? None of this is normal arithmetic. We have to have all these interesting column types that we surround all of our normal arithmetic types with. Of course, right, Slick has the same problem, but at least in Slick you have equal, right? At least in Slick, you have this complex type class system behind the scenes that can give us more illusions of normalcy. Right now, sorry, Kotlin doesn't have that. Okay, right, EQ, right, here's DSL noise, here's more DSL noise, here's DSL noise, here's DSL noise. Like, okay, half of this query is turning into DSL noise. Okay. Why can't we just do a when clause, right? Kotlin has this nice thing called a when clause. It also has an if, but an if is actually just a when clause. So, this is perfect. This is a wonderful, wonderful construct that we would just love to translate directly into SQL, except for we can't. Remember, let's actually look at this thing. What goes in, what comes out? Two types go in, one type comes out. Okay? There's the signature. To a runtime system, everything that's a function signature is a complete black box. A runtime system can't see inside of arbitrary function signatures. It can call them, but you can't see inside. Right? This is actually, by the way, in Spark land, this is a gigantic problem. Okay? If you've ever had the misfortune to deal with Spark query plans, you will immediately be able to tell what Spark query plan came from a query that could not be optimized because you'll see all these barfing icons in the query plan. Actually, you won't. What you'll see is you'll see a bunch of serialization steps that are completely unnecessary. And on top of that, you won't have any predicate and filter push down, just by the way. So this is a huge problem in the JVM and a huge problem in compiled languages, in general. Okay? So part A, we cannot see inside of a function signature, which is why we can't use normal language constructs in order to build things like SQL queries, because we can't reify them. And of course, that means we have to go to DSL land and the hell that entails. Part 2, even if we could do it, even if we could see inside of these black boxes, how the heck would we know that we'd actually translate the stuff inside into a real SQL query? Like, what if they do things like type checks? What if they do type checks? You can't translate that into SQL. What the heck do you do with that? Second question, right? How do you know that this translation would actually succeed? So the answer to both of these is one thing. Do it in the frickin' compiler, right? Metaprogramming or a compiler plugin can actually see what is inside of arbitrary function signatures, right? We did this in Scala with metaprogramming in Scala. We can do this with a compiler plugin, right? This is the internal IR, right? This is what the compiler actually sees inside from a construct that looks like this. And we create an architecture based on this. And then we take the language level intermediate representation or the syntax tree or whatever you want to call it, we take that, we translate it into a bunch of other things. This is the ExoQuery syntax tree, I call it the XR. We take that, run it through a series of basically transformations, which I call the query compiler, run it through a system of tokenization, eventually we get SQL out of it. Okay? And the result is something like this. Right? Here's the happy path. We've got a happy path. Let's there's our where clause. We basically use a quotation operator, which is the capture, right? And then let's take that, capture it into a variable or an identifier, take that and use it in a query. Right? There it is. A pair is a Kotlin tuple type. And let's use it in there. Let's build it. Let's run it. And there's our SQL query that came out at compile time. Also, you can use it. You can grab it in a file. I've also generated a file that. Thank you. The unhappy path. All right. Let's look at the unhappy path. Let's try to do like a type check inside of here. And there it is, right there. I will immediately give you a compile time error. The second that you do something that I cannot translate into SQL, you immediately get a compile time error. So this is ExoQuery in a nutshell. So here's what we saw before, right? This is a captured function that it has a conditional, and we use this. I can't go into captured functions. They're basically captured lambdas, which is a complex topic. I cannot cover it today, unfortunately. But let's splice that into the main query and see what that is. Okay, so there's our where clause, and there's the query that produces. These things are simple case classes. These are simple case classes that go in. We might have to make them serializable, that we'll talk about later, but simple case classes go in, and SQL comes out. We do not need column types. We do not need any of that sort of nonsense. Now, this is, of course, what it's based on. Right? Everything is inspired by Microsoft LINQ. I can't do something like this because I can't control the lexer, right? And I'm not a multi-billion-dollar corporation, so I can't do that, right? Quill does it like this, but of course in Kotlin we have no for comprehensions. But at the end of the day, the for comprehension actually turns out to be more of a limitation than a benefit, believe it or not. And I'll go into that. So here's ExoQuery, right? Here's the syntax. And oh yeah, there's the shortened form, right? Because for a lot of the time you will want to do a capture and a direct style in one, right? So there's a capture, there's a direct style. I'll show you an example of a capture without direct style in a minute. Okay. Now, right, you might ask, is this some kind of gimmick, right? What is this exactly? What is this thing that I just create some values from and I just select things from it? What is this exactly? So if you're familiar with direct style, you know where I'm going, but so if you do, bear with me, but there is a lot of thought put into this. So this is real. This is a system that is as real as Microsoft LINQ. Let's take a look at Microsoft LINQ again, right? This, right, normal collection types go in, these are the row types, normal row types come out, normal arithmetic happens inside of it. Now, this is what it actually translates to. Anybody recognize what this structure is? Anybody? Right? Well, I'm pretty sure at LambdaConf we know what this structure is, obviously. Oh, call my bluff. It's actually not nested like this. It's actually flat like this if you've read about LINQ. You know that it propagates all of the alias, but it's actually flat. Oh, wait, monadic structures are isomorphic. Their flattened form is isomorphic to their nested form, which is, of course, why Microsoft decided to flatten it out, because they were concerned with performance. Okay, fine. Right, so this is the same thing. And again, normal types, right? Here it is in Scala, right? C#, Scala. Select many as flat map, select as map. Simple as that, okay? Again, sugared form, right? We understand what the types there are, and this, of course, leads to Quill, right? We create joins. Why do we create a special construct for joining? Can't we use just regular conditionals? Oh, we need left joins. We need left joins that are able to have optionality or nullability or whatever you want to call it, right? Ideally on the level of the whole row, right? That's why we went this direction with Quill. But of course, we can't do that with Kotlin, no for comprehension. So this is where we go to monadless, right? All of this stuff is, by the way, inspired by Flavio Brazil. Like everything here is inspired by Flavio Brazil. Like I built Zio Direct, but of course it was inspired by monadless. It's all Flavio's inspiration. But anyway, so okay, all right. And by the way, this is not arbitrary. These constructs are not arbitrary. They have to follow a very, very specific set of rules. Most notably, this is a talk that I've given on Zio Direct. Most notably, there needs to be sequencing. In particular, inside of ExoQuery, there is only one bind per line, which is even a stricter requirement, but there's no bind. There's actually no explicit bind, which I'll show you in a minute. Okay, but bottom line, these constructs are extremely tightly controlled, and only by extremely tight control over what goes inside of this clause, right? Only by extremely tight control over what goes inside this clause. And you've seen what happens if you violate any of the rules. You get a compile time error immediately, okay? Nothing runtime. But if you follow an extremely tight set of conditions, then you have an isomorphism between these two. And again, normal types go in, normal types come out. Those variables just have plain row types. Now, we need just one more step until we could create something that is really a lot of fun, which is this. A from function can be a flat map or bind, and then the joins can actually do both. Because if you've ever thought about what a join is, you don't actually need to ever do anything other than a bind after a join, right? By definition, a join is a filter and a bind, right? Because every single join is actually just a subtype of a full join, right? So you never need to do anything other than bind at the end of a join, so that means it can be implicit. And you can create a syntax that is fully monadic, that really looks like SQL. That really, to anyone that is looking at this thing, you don't need to know anything about monadic laws, you don't need to know anything about fork comprehensions. It's like, okay, this actually makes sense. And again, the types that come out, normal row types, these are just case classes or data classes or whatever you want to call them, right? The arithmetic in here, again, normal primitive types. This is my equivalent of a collection type. This is the equivalent of query in Quill. And here's the most important part. The query is not built from this. It's built from this. This is built from this. It is built from the desugared form. And this has extremely important consequences. First of all, it's compositional. You could do this, or this, or this, or this, or this. Mix and match, all of them in between. More importantly, in the first clause, we have flattening. So if you have a nested construct in your first clause, we flatten it. So here, right, we have a nested construct. It is actually flattened. And this is extremely important because if we have nesting or more nesting inside of this first clause, it will flatten them out, right? It will flatten all of this nesting stuff in here. It will flatten it all out. Now, you won't write code like this, but you'll probably write code like this. Right? This is what you will actually do normally, right? You'll have a sequence of things that you'll compose. You'll say, oh, make this kind of piece of query, and this kind of piece of query, and this kind of piece of query, and this kind of piece of query. Oh, dump them all inside of my main query. And guess what? Systems like Slick will give you a gigantic, nested, incomprehensible thing whose performance characteristics are horrific, right? This is why it's extremely important to have these kinds of constraints so that you can create flattened structures, okay? And because these things are logically isomorphic to their nested things, the whole thing works out, okay? And there are academic papers on this, by the way, that actually compare different query types, flattened queries versus nested queries, and the conclusion is that the flattened queries are way, way better performance because you think about how a database optimizers actually run through this thing, right? A database optimizer cannot make the assumption that anything is a pure function. A database optimizer cannot make the assumption that anything will evaluate consistently to the same thing, for example, if it's a view. Okay? So database optimizers have to make some incredibly stupid assumptions. And based on those stupid assumptions, they create these kinds of query plans that can be extremely inefficient. Okay, which is why, and you think about, for example, how Prolog or something like that would actually look at every single kind of thing that every single part of an inner nested query can be. You immediately understand that this kind of thing makes a Cartesian explosion if it's like 4 or 5 levels deep nested. Okay. So this is why having flat queries is extremely important for performance. Okay? Some other interesting consequences. You can create domain-specific join functions. Again, this is a advanced ExoQuery topic. See me for the advanced course in ExoQuery if you want to understand exactly how this works, but you can create domain-specific joins. On top of that, we can do full joins, right? We just do froms, and this is a full join. Okay, so some very, very nice consequences of doing it this way. All right, so ExoQuery is as real as Microsoft LINQ. Let's take a look at some of the features that I quickly ran through. Okay, all right, again, regular case classes. This table thing is just a constructor of SQL query of T. That's what comes out, by the way. And why does it work this way? Right, because capture functions need to be able to capture all of the inner contents. And by the way, you cannot do the table function outside of a capture. In fact, you cannot do any of the ExoQuery DSL outside of a capture. Kotlin, one of the things that Kotlin does really nicely, actually, it's able to capture nested operations and context-based operations without forcing you to do things like type classes. It has very nice ways of doing that. So this system takes advantage of that very, very intensively. Okay, so let's just plug it in. So that's what your typical query will look like. Okay, there's the type that comes out. It is a simple Kotlin pair type. And when we take this thing and we evaluate it, what comes all the way out from the other side of the evaluation is a simple pair type, simple tuple type, right? What you see in the type signatures is what's going to come out. We don't have crazy table types. So here's left join. What does left join do? Ooh, look at that. Kotlin has this very nice way of doing nullability. And left join will do that. It will actually create a nullable type. And the nullable type will come all the way out. Again, just like for regular types, it goes all the way through. For nullable types, it goes all the way through also. Next up, you can actually take nullable types and you can select from them. You can select multiple things from them. All of these things will work. All of these various projections of nullability will work the way that you expect them to. You can even do defaults. And defaults will translate the way that you expect them to, and they will undo the nullability the way that you expect them to. All of this idiomatic Kotlin that doesn't work in any of DSL land, that doesn't work in KTORM, it doesn't work in Exposed, it doesn't work in all these Kotlin ecosystem libraries, all these actual idiomatic Kotlin constructs, they will work in this system. They will actually work in ExoQuery. Next up, woo, this is a nice little thing here, right? I am no longer bound by the rigid properties of for comprehension, so I can actually put in structures like where that don't require assigning variables, or group by multiple fields, sort by, and all of this just works. It is very nice. It is very nice to be unchained from for comprehensions, actually. And this is all of this is inspired by direct style, all this is inspired by monadless. Now, let's have a look at, from, right? This is just a from clause. This is just a from clause that's selecting a row. Okay? Right? Table T is an SQL query constructor. Oh, okay, look at that. Right? That's what comes out. And these are isomorphic. This is the capture I was talking about before. This wasn't the direct style capture. This is the applicative capture. Right? Here's the direct style capture. This is the applicative capture. They are all isomorphic. And again, this goes back to the LINQ design. This goes back to the design coming from LINQ, where you have a direct style syntax or an SQL style syntax that is based on sugar from the select and select many applicatives. Okay, and let's take a look at some of the applicative operations. Okay, normal filters. Correlated subqueries. We can do correlated subqueries, and they will just work normally. And, of course, map, right? Functors. They are funky functors. I allow this. Some people would be horrified by this, but no, I allow it. This is fine. This definitely makes it into a funky functor when you think about the type signatures of these aggregator operations, but no, this will work just fine. Distinct. Distinct works. Limited offset works. Union works. This is a very important pattern. mapping to a common type. This is the polymorphism right there. This is the common polymorphic type that will be passed to downstream joins and downstream constructs. Here's an example, right? You'll compose a series of things that you will then pass into downstream types, and look at how all of this is flattened. Look at how all this is flattened, right? We don't have inner nested selects, which would be the naive way of doing this. We do not need to do many different kinds of projections, even though we are projecting. It flattens it all out. Now, okay, let's take a look at how we actually get data inside of this, because presumably, if we've ever seen quoted, there needs to be data that goes inside, right? At one point or another, we actually have to deal with real runtime data. How the heck do we deal with that? And ideally, we don't want to be subject to this problem, right? Ideally, we want to be SQL injection proof. Okay, what do? So this is essentially a lifting operator. This is how we get parameters inside. Now, ideally, what this is supposed to do is it is supposed to actually take this thing and propagate it across many layers and ultimately get injected into a prepared statement of some kind, whether it be a JDBC driver or some other kind of database driver, right? You need to actually propagate this. Now, this gets interesting because what happens the second that you have user-defined types? Because they exist, right? In functional programming, we love to create types for emails, or we love to create types for IDs. How the heck do we do that? Well, in something like Scala, we would have a type class-based lifting system. We do not have that in Kotlin, so I use idiomatic Kotlin serialization to do this. So, effectively, you write a serializer. Now, by the way, one of these interesting things about this approach is that you can do mapping to primitives independent of the actual database technology that you're using. This works with JDBC. This works with Android support SQLite database and SQLiter on iOS. But anyway, I'm getting ahead of myself. Right? This is independent of database technology. Now, of course, any functional programmer will be very, very annoyed at this. Okay, right? We're used to our maps and our contra maps, which is why I'm working on a syntax that works more like this, that is slightly more pleasant. Again, advanced topic. See me in the advanced course, about the advanced course if you want to know how this stuff actually works. And one other thing. Kotlin X serialization supports low-level serialization, which basically is a way of telling the Kotlin X serializer, yeah, I can't do this, you go deal with it yourself. And the low-level implementation of the decoder will have to do this. In other words, you'll have to actually write a JDBC-level decoder. I support that too if you really want it. Next, the other problem. How do you get data out? Right, same kind of thing. I use Kotlin serialization. You annotate your stuff as serializable, and the stuff comes out, which means that you have to make everything that this thing could contain serializable, but it is actually possible to have a very wide variety of user-defined types, so long as you annotate them appropriately. Again, this is Kotlin. You have to use annotations. Sorry. And you might have to annotate it occasionally with my own annotations right there to tell the ExoQuery system that this is a value type. Not always, but sometimes this is necessary. Again, sorry, advanced topic, can't go into it more. Bottom line, Kotlin X serialization is the closest thing that Kotlin has to generic derivation. It is not perfect, but it is pretty darn good, right? I'm doing this so I don't need reflection. This is how I get out of JVM reflection, and this is how I get out of the frickin' JVM. This thing works in Kotlin multiplatform. Okay, you can use this thing. This produces native binaries on Linux, on Android, on iOS. You can use ExoQuery on iOS. I actually have a code sample right there where it actually has ExoQuery running on iOS and Android, and you use the same set of database controller functionality. And here's the interesting part, right? Compile time queries are ideal for native environments, are ideal for mobile environments, are ideal for things like serverless, where you don't want to be spending CPU cycles to run a query compiler inside of your app. right? This is ideal for those kinds of situations, right? This essentially, this capability is a perfect fit. It's ironic, actually, because, you know, in Scala, all these techniques that we've built up over the years, not having to do runtime reflection on the JVM level, not having to do nasty type checking on these class objects in the JVM. All of these things are actually a perfect fit for native, a perfect fit for mobile. It is a tragedy that Scala has not managed to target these operating systems in a commercial way. But this is why I'm doing Kotlin. This is a second chance. This is a second chance of using the kinds of techniques that we've developed and using them in a way that is substantive, in a way that actually can reach the market in some kind of substantial way. Okay. Now, a couple of other topics I'll cover. Actions, right? At some point, you actually need to write things to your database, not just read from it. Well, here's an insert, right? Again, the context inside of this expression is this type. The this pointer inside of here is this. Because again, Kotlin has some very nifty ways of projecting context. Now, that means that you could just plug in variables like that, right? Most of the time you won't be hard coding them. Most of the time you'll be using parameters. Slight caveat, you might have name conflicts, so make sure to avoid that. I'll give you a compile time error for that. Now, presumably, you will not want to specify every single parameter inside of every single data class over and over and over again every single time you want to be able to insert something. Remember, data classes or case classes inside of corporate environments can be over 100 parameters large. Okay? So yeah, that's a problem. How do we do it? Well, this does it. Set params effectively sets all of it. Ooh, but there are some things that we don't want to insert, right? Like ID. We expect to have database-generated IDs, right? So there's an excluding function for that. It is variadic. You can put whatever you want inside. Next up, we have a returning function if your database supports it. Right now, this is supported on SQLite. This is supported on Postgres, and this is supported on SQL Server. SQL Server has a slightly different syntax, but it works. Returning clauses, right? We can do returning clauses, and we could return not only IDs, and by the way, again, the types will go straight through. The types will come out exactly the way that you expect them to. Not only can we return IDs, we can return arbitrary objects, and we can even return arbitrary objects with expressions inside. The Kotlin serialization will take care of all of this. Okay? And again, advanced ExoQuery topic. I cannot go into this anymore, but you can actually even have SQL queries in the returning clause for Postgres. Anyway. Not universally supported. Here are the databases that support them. If it does not, what you have to do is you have to use a driver level construct called returning keys, and that does it on the driver level using this prepared statement.generated keys. You can actually also do various kinds of custom types inside of here. I can't go into it, unfortunately, right now. Okay, next. Right, on conflict update. At some point, you might also want to do an upsert or two. Upserts can also have nested complex expressions. And I support that on Postgres, MySQL, and SQLite. Again, you can actually do complex logic inside of these upserts. What else? On conflict, do nothing. That'll work. Next, update. Update queries. Same syntax, right? Set parameters, excluding, all that works in updates. Returning works in updates if your database supports it. If you want to actually update all your rows and not have a where clause, I make you explicitly state it because I have been bitten myself by this, of having of where clauseless updates, so I will actually make you do that. And deletes, same kind of thing, same kind of syntax, right? Also supports returning if your database supports it. And yeah, you'd better the heck say .all if you want to delete everything inside of your table. Okay, batch. Right, we support batch with on-conflict update and returning, and all of these other constructs. Batch queries are supported for all of these different things that you would expect to have. Okay, and all of this works through JDBC. Unfortunately, right now I only support batch in JDBC, and it works through this add batch and execute batch functionality on the driver level. Now, could we do better? Could we do better? Yes, we could. And batch concatenation is the way to do it. right? Actually concatenating all of the variables, but there is a problem. This is extremely complex functionality to implement. Right, first of all, there is a limit for how many of these question marks can go inside of different databases, which means how many of these queries you need to execute. And by the way, this limit is different for every single database. Okay, do we inline it? We could directly inline it if we're not worried about SQL injection. In many corporate environments, we actually have trusted data going inside of these, so we don't really care. But what do? We need a decisioning component. I tried doing this. I tried doing this in Quill. It didn't work. It didn't work. Too many things broke. It was too buggy. And this is beyond the ability, right? We need to have a whole ton of constructs to define what this is, and they need to work with all of the existing functionality of regular inserts, updates, and deletes. This is the limit of what open source can do, which is why I'm planning to launch a commercial offering, a professional offering of ExoQuery Professional that will have all of these features that I've always wanted to implement in language integrated query that will actually have very nice optimizations for blazing fast batch concatenation, inline parametering, dynamic columns, next level of query optimization flattening, more DSLs for insert into select and updates and schema DDLs, being able to do things like create a database from a query, because I can actually do that. I can create right now, by the way, this is something that you can sort of kind of even do in Quill. You can create a whole database from a single query, because embedded in the query are all of the types that you need to know. So you can actually create a table from it. And not only that, you could run the query on that table and you could get performance metrics from that. Wouldn't it be nice to actually have that? Wouldn't it be nice to actually have that during the build cycle? Every single build cycle, you actually can go into every single query and get performance metrics. And if you messed everything up, you can compare it to the last one. Right? This is what I've always dreamed about doing. This is impossible to do in open source. Right? I need to actually hire someone to think about all of the edge cases of all of these constructs. This is the limit of what open source can do. I've tried it in Quill. It doesn't work. That's why I'm going to be building a commercial offering that has these features. And I'm telling you up front, this is the feature set that the commercial offering will have. There will be a large set of features for the open source offering as well. I will actually integrate this thing into Spring and Hibernate. All right. We as Scala developers have long despised many of these things, but I am tired of keeping my head in the frickin' ground. I plan to integrate into all of these systems because guess what? Market adoption. At the end of the day, these systems work. At the end of the day, Spring solves a very large set of use cases in a way that is good enough. Same thing with Hibernate. It solves a very large set of use cases in a way that is good enough, and I want to integrate into these systems. I want to also have a bunch of different ergonomic improvements, support for JavaScript. That is the only Kotlin multi-platform target that I don't support yet. I want to support that. I want to support Oracle, and a bunch of other things. For example, code generation coming from a database, control for queries on the level of entire units of queries, potentially. Oh, for all these queries that exist within a file, right? Because that's the way that queries I've seen in Quill being organized, right? One giant file with hundreds of queries. For every single thing inside of here, we might want to do certain kinds of things, like turn on certain optimizations or turn off certain optimizations or have certain naming conventions, right? Wouldn't it be nice to be able to have that on a file level? Wouldn't it be nice to have file level control over this? Well, okay, right? We would use type classes, we would use implicits, okay? Sorry, these things are not things that the masses will use, but guess what? A file level annotation does quite well for this kind of functionality, especially when you think about the issues and dilemmas of intent versus mechanism. Anyway, so I've got a large set of open source features planned. Now, very quickly, the grand finale. Remember this guy? We talked about him at the beginning. Okay. All right. Well, let's see if we can solve this using ExoQuery. Right. Here's our two tables: merchant clients and service clients that we had at the very beginning. Here's the join. Here are a bunch of other things that we really don't want to care about that are involved in this query. Again, they all come together in this final union, and this is the output. This is the output of the inner union and the nesting and then the joining of the account types and then the entire projection that comes out of that. This is the result. Well, here's one query. Here's the query for one of the inner unions. Here's the query for the other. Here is the actual combination of the two. Right? Again, normal types. Completely normal expected types. Remember how I told you about a pattern that I used before? Mapping to a common type and then taking a union of the two. Well, that's exactly what I'm using here. Now, take that, plug it into, as an argument, plug it into the outer query. Well, there we're actually doing the plugging down here. And there we go. This is the query that it produces. And it works at compile time. It produces this gigantic thing at compile time. Now, if you want to know that this is what we expect, you could take a look at those. Basically, it's all the same. The only tiny difference here is that it has to actually do outer projections as opposed to this thing. It's the same thing. Creates the same constructs, outputs the same data. Now, one other thing. Nested, right? I didn't tell you about that, right? Nested, you can actually force nesting of inner queries. This effectively blocks the query flattening optimization. What happens when we don't have this? Oh, that's right. Remember how we had an inner union and that inner union was joined to some other tables and joined to an account mapping? What if we take that and we flatten it out? Better performance. But the thing that it creates is an utterly incomprehensible query. And by the way, if you've ever talked to any DBA, they will eventually tell you that the best performing queries are human incomprehensible, which essentially means that SQL is an assembly language at the end of the day. Okay? Which is a very good case of synthesizing it with systems like this. Bottom line, this is what we were looking for. This is the kind of abstraction that we were looking for. This solves it. This gives us the abstraction. Language integrated query is the query composition abstraction that we are looking for, and ExoQuery does it for you. So, quick recap. I talked about the need for abstraction in databases and how it's impossible. How no solution exists in Kotlin that is anywhere near tractable, how you need something which is a language integrated query solution that takes functional programming foundations to the core, how ExoQuery delivers this functionality in a way that is elegant, in a way that is powerful, and synthesizes the toughest queries that I have seen in my career fairly easily. Thank you. Those are the slides, by the way, if you want to see them.
Thank you, Alex, for this journey into ExoQuery. We have time for one question, if there is any. Yes.
Dustin.
So you were saying something, so the query compiles to the SQL at compile time?
Yep.
How does that work in Kotlin?
Compiler plugin. I use a compiler plugin that essentially runs code during the compilation of the actual Kotlin code.
Ah, I see. That's interesting. Okay.
Yeah. It's the closest thing you have in Kotlin to metaprogramming.
And you made a point about doing this on native devices, and you said Scala couldn't. What was that?
Well, because Scala never had a serious offering for, Android, let alone iOS.
Oh, I see. Okay.
Yeah.
Got it.
Thank you.
Thank you.